morning. Good stuff. So this is based on a bunch of work collaborated with my PhD students, Atri Rudra and Jess Grogan, a bunch of undergrads, with collaboration with Atri Rudra at Stanford, in particular, Simran Bedi, Sri, Sabri, Dan, Albert, and Cherry. If you have a question on how to build deep learning systems based on the idea that I'm presenting, please don't ask me. I don't know, but everyone on the last slide is a much better person to ask this question. I can try, but I can almost guarantee my answers will not expire. All right, so as you've already seen, bunch of talks, we already know the function norm, transformers and function. But there's actually been an explosion of alternatives, kind of like transformer-free architectures or some quadratic architectures. Here's a table, kind of stole this from my collaborator Simran, from I think 2018 to 2021. Which is a bunch of other things. To be honest, I don't even know what all these things are. I know some of them, so I know this is like Mamba, for example. But the point is, it just seems like at some point it was like every day there's a new architecture out there. And so, like, how is there a canonical way to think about this? And if you want to take one thing from this talk, my hypothesis is yes, arithmetic are one way to do this. So, an overview for the rest of the talk, I'll quickly go over the setup for this audience. The standards, so I kind of quickly go through it, make some assumptions along the way, very informally define arithmetic circuits, then try to kind of quickly make the case that they're general enough in the sense that they can represent all of these various alternative architectures. I have a star here because I'll be lying a little bit here and there, but morally, it's all good. And so, as you all know, kind of transformers are kind of two basic kind of layers, the MLP layer and the attention layer. I'm going to talk about how you can kind of replace them with something. And both of them turn out to be quadratic in different parameters, and kind of how we can do it. All right, so except for maybe the last slide, I'm just going to assume that the focus is on language modeling tasks instead of next token prediction, right? So, for example, Barack and Michelle have all went to Harvard to visit the daughter, and you're pretty much saying, Malia. By the way, this slide is Dan Fuad stole a bunch of slides from a collaborator as well, various acknowledgements of them. So, again, should be standard, but just in case we just kind of wanted it here, the way to think about a sentence is kind of break them into words, tokens, and then kind of map each of them using an input embedding onto a vector of length t. Right? And I'm going to use n to denote the sequence length, which is the number of words or tokens. And I think this is PyTorch notation, like more tensor notation, instead of the standard n cross d. I think when I was making the slides, for some reason, I could not figure out the cross thing to put in the subscript properly. But it turns out this is standard in some notions. I'm just going to use that. So n is called the sequence length. D is called the model dimension. And what kind of functions are we interested in? We're looking at like the sequence function. So you give an n cross d matrix of this, but we get other things there, right? So we saw an example, a variant of this in Daniel's talk when he talked about the associative equality function, right? If you bunch of tokens, you map, say, the ith token to the jth one and then output the jth. Okay. Okay. And even though kind of, want to kind of, these are used in this next token prediction kind of thing, I'm just going to go back and like autoregressive model, like simple, you have a model, you have a bunch of parameters, and you have input. And the inference problem is you kind of fix the parameters, and given x, you put the corresponding output, right? And you hope if your model is good, then the output tracks the function that you're interested in. On the other hand, training, your input is fixed or more precisely given bunch of inputs, and you want to compute the parameter that minimizes some error, like point error or something. Okay. There is a way to convert all of this into kind of this token generation thing. For example, your model is causal and stuff. Again, you all know about this more than I do, so I'm just going to go over. One assumption that I'm going to make, which is true in practice, is in general, of course, you could learn kind of these models from any algorithm that you want, but in practice, everyone just uses gradient descent. So from now on, whenever I say training, I will assume we have to use gradient descent. And so one of the kind of computationally expensive parts of this is to compute the gradient of what we follow. So again, just in case, gradient is just computing all the partial derivatives, and in this case, with respect to my parameters. So I want to talk about how you can kind of have efficient models, and I'm going to make a simplification and say the notion of efficiency is just the number of parameters, with this addition and multiplication, and that allows us to think of, and this is kind of the view I want to quickly present. You can think of model as arithmetic circuits. Right? So how do you think about this? Well, the inputs now are the actual input and the parameters as well. And then you model the addition and multiplication and so on. So in particular, if you kind of take, say, any of the transformers, Mamba, or any of these models, the kind of arithmetic circuits that you get is kind of a slightly stronger notion than the kind of formal definition where the structure of the circuit is fixed. Right? So if you think of the transformers, the way things connect is fixed, but the kind of model ways that change. Okay. So arithmetic circuits, what are they? These are the circuits where all the gates are addition. So for example, here is the discrete Fourier transform of order 4 by 4. And here's kind of what's called a linear arithmetic circuit. The gate actually is AX plus BY, where A and B are. Want to begin? Wow, so this is one result. How many of you are familiar with the Bauer's transform? All right. Oh, good. A lot of you. If not, here's the kind of really amazing result. It says, if you give me an arithmetic circuit for this model, and you want to compute the gradient, the arithmetic circuit complexity is up to a factor of 3. For addition and multiplication, you can add division, bulk and stuff. So it's a really nice result. Keep this result at the back of your mind. We're going to pull it out towards the end of the talk. Yeah. Also, if you've not seen the proof, it's basically that propagation. What do we lose? The first thing to note is if all your gates are addition and multiplication, what you end up is a polynomial. What this means is you cannot express all models exactly. Like even if you do NLP, you have a ReLU or something at the end, that's not a polynomial function. But this, to me, is not a big thing, and like especially since ReLU use GNU or something which is smooth, you can approximate smooth activation functions by low degree polynomials. So it's not that unreasonable. The thing that is really unreasonable when it comes to practice is the nice thing about arithmetic circuits is you have infinite. Really nice if you want to think about and not worry about actual practical problems. For example, the vanishing gradient thing. Right? So moving from arithmetic circuits and actually implementing it in numerical stability issues becomes something that you have to manage. Okay. All right. Yeah.
For softmax, you're also approximating with the.
Right. So softmax, there's the division thing, which is like because if you don't normalize, it's exponential, and then you can just approximate the x. Right? A low polynomial. Again, assuming the e to the x is small, right? Yeah. But I come to that point, and Josh is going to hammer on that point, I think, even more in stuff. I think, I don't know what else he's talking about, but I am guessing from this stuff. What I want to kind of quickly go over is kind of talk a bit about some of these architectures and kind of quickly try to make a point why these are arithmetic circuits. And David has explicitly kind of point out why transformers, the way they are actually not really explicitly because they're not polynomials, right? So again, we've seen this definition a few times, so I'll quickly go through it. Familiar. So again, the transform architecture actually has lots of pieces. I'm going to just focus on the feed forward or the MLP layer and the attention layer. Feed forward, the way to think about this is you have your input X, you multiply on the right by a D cross D matrix, you get another D cross D matrix, you just apply the component by value or some activation function. The attention layer, you kind of map, multiply Q on the right by 3 D by D matrices. You get these queries, queries T and value matrix, you kind of UK transpose. You should take the softmax for desktop. I'm just going to assume it's component wise exponential. So I'm ignoring the normalization. The thing to note is the MLP layer, since you're multiplying on the right, it's only acting on columns. The attention layer, on the other hand, acts just on the rows. It's kind of mixing, in one case, the sequence length dimension, the other case, the hidden dimension. It also turns out if we kind of just look at it for a little bit, the attention is permutation is varied. So people use positional encoding for embeddings to do this, which I'm going to completely ignore in the start. Okay, so the model that the way I think of transformers is just here a bunch of attention and MLPs following one another, right? And again, if you want to think of parameters, what are the parameters for each layer? You have kind of the Q prime, K prime, B prime from attention, and the W from the MLP, and so these are all the parameters that you learn. Okay. As David pointed out, like this is not an arithmetic circuit precisely because of these kind of softmax and already things, but if you ignore them, I'll come back to why ignoring them might not sound as bad, at least in theory. But why focus on these two operations? It turns out, and this is slightly, this is 21, I think the numbers have changed, but like the trend is still the same. If you look at kind of the time that's spent one clock time or flops, like these two operations are the bulk of the computational. So is there anything? So as we've seen, transformers are used in bunch of applications. The things they can't do is a trivial answer, but since they can't run in support. Part of this answer is trivial. So it's easy to argue that the feed-forward layer needs omega d squared time and space, and the argument for that is well, you have to multiply with this d cross d matrix. I have to read it. So that's easy. If you look at the attention thing, there seems like, well, this also should be n capital N squared, because, for example, if you were to compute UK transpose, you could materialize this n cross n matrix. But that's not alone. Maybe you can somehow do some magic to kind of combine things. But it turns out you cannot under strong exponential anthropological theorem. Result that et al. Showed that you need n square time, and then Josh has a bunch of strengthening of the basic assumptions that are needed. So transformers are quadratic in both the sequence length and in one dimension. This is of course not new. People realized this very, very early on, right after transformers came out. So there's a bunch of work in approximating attention, low rank, bars, all kinds of stuff. Again, all if you kind of sit down and write them down, you can all write them down. So I'm not proving this to you, just take it and take it. Okay, so the thing that I want to cover, from my understanding these days, there are kind of two broad classes of these transformer principles. One is based on what's called the linear attention stuff, and the other is based on state space models. So I just want to quickly go over them. So what's the idea in linear attention? So first do stuff that I said to do. It's like just ignore this explanation. So let's assume I just the QK transpose strategy. Nice thing about matrix multiplications is they're associated. So you kind of compute Q transpose times B. And so now you have an n cross D, sorry, D cross n times n cross D. If you do this multiplication first, the cost goes to D squared n. So you've gone from n squared D to D squared n, and typically D is smaller than it, like at least less than squared. So this gives you a lot of savings. So it is fine if this is how you want to do it, but if you just implement this whole strategy. And so the intuition for why something like this might work is you go back to Taylor series, exploring the Taylor series expansion of EBX. For example,
Did you coordinate your shirt?
yes, But only after a case, it happened to be in mind. So, so you could, for example, approximate e to the x with the degree 2 polynomial like this. This, of course, is only good when x is between 0 and 1. But for example, there's, this actually has been implemented in practice, at least in experiments with folks well. And the observation is, well, if you do it this way, if you're looking at Q times K transpose, taking the x from that, each entry corresponds to exponentiation of some row Q in capital Q and column, column. Sorry, a row in Q and row in K or column in K transpose. Right? So you get kind of this equation. And so then if you think about this, this is basically you're taking QK transpose and doing like component by square, doing this and adding stuff. This and so in particular, you can define a map. And this, for example, the earliest thing that I know is explicit that was about Pinova alone. That said, if you take a low degree polynomial, so if you're the low degree is Q times K transpose, you raise each entry in this low degree line by low degree polynomial, then the rank doesn't grow too much. Right? So if the original rank here was D, and you're like degree 2, then you get like D squared. And so in particular, for example, if you use this formula over here, you can have a map that instead of now maps to like 1 plus D squared. So you've increased kind of the hidden dimension, at least for Q and K, slightly D squared. But now you can just, instead of D squared over here, this turns out to be D times F times M. And so you then again have to compute the state that you saying associated things with kind of. So as mentioned, Josh has a work that kind of pushes this in some sense, I think, to the limit. And so I don't know, Josh, I'm presuming you're going to talk a little bit about this. If not, read his paper and have more on this. Okay, so that's kind of one thing. The thing I want you to remember, in this case, for example, kind of this map turns out to be a polynomial map. So again, everything is polynomial. So all right, state space models been around for a while. If you were in Uncle Starks, like much more specific case of a hidden Markov model if you really wanted to go that route. But so what you have is you think of this state space model as a sequence of input x1 and so forth, and your corresponding output to y1 and so on and so forth, and you maintain the state as you go along. We'll assume that the state is of size n. And this is, I guess, in the state space model, you do linear updates. Right? So the new state is some matrix multiplied by the old state plus some kind of update based on the current value. And then you again do a linear function to read out the output. Okay. So it turns out, from Albert, Ashis, and a bunch of us, that basically observe that if you unroll this recurrence, what you get is a convolution. So you can, the nice thing about convolution stuff is you can do stuff in parallel, you can training and all that. But again, in fact, it's a linear map over here. Albert then has this book S4, where it's basically the same as here, but careful in picking how you bring this data say. And then how many of you heard of Mamba? Okay, so it's followed by Tree and Albert, where they instead of, so the difference is originally this A, B, and C's were all fixed across all I, and they now make it dependent on I. And the kind of dependence is kind of linear on the input. So these linearly depend on the input, and so again, I'm cheating a bit here. There are again multiple moving pieces in Bamba. There again are non-polynomial activations and so on and so forth. But if you kind of think of at a high level conceptually, all right, so again, as a reminder, so I don't know if convince is the right word or not, but maybe all these things that exist, you can think of them as arithmetic symbols. Okay, so again, as a reminder, transformers is kind of these MLP and attention layers. And the way I want to go around for this, how much time do I have? 20 minutes. That should get like how to replace this MLP layer with something that's subquadratic and then replace attention with something that's subquadratic. Not because that is pedagogically the best way to do it, but that's how we did it. So I'm just gonna go with the flow there. Okay, so I want to replace the MLP there. But before I do that, if there is one thing you should remember from this talk, other than arithmetic circuits are great, is that these models are run on kind of hardware that's specialized for AI, right? For GPUs and TPUs. And that makes a lot of difference. Specifically, you can design all. So I showed you a bunch of these kind of, I should have done this like run the regular expression star formula and see how many papers actually satisfy that. I think it's going to be in the hundreds. But many of them, like using low rank sparsity, the idea was you get reduction in flops, right? Pretty much by definition. But when you actually ran them on hardware, they're actually slower than transformer detection. And that was because they were not paying attention to kind of the fact that these hardwares have very specific. It's actually quite fun to think about them. It's like thinking of your favorite algorithm in a new computational model. So I actually kind of find that fun. But the way things are arranged, and I think Christopher gave his talk yesterday kind of talked about quickly. So you have kind of this memory hierarchy in these things. So the way to think about this, you have this high bandwidth memory, which is slow. You have more of it. You have slower, smaller, faster memory. And then in general, there's more, as you might imagine, right? So there's caches and stuff, but let's think of two levels memory. So you start up with an input that starts up in the high bandwidth memory, you kind of pull it into these compute nodes, kind of do computation over there, and then you write the answer. Okay, so in this view, what really matters is kind of the data transfer over here. And in theory, you have to study this for a while, the input output complex. Okay, so maybe a few more things to keep in mind if you are kind of thinking of creating new algorithms that you want to run. And there are other things you want to keep track of, in particular, all the atomic operations that happen on these pages. So you can think of like 8 by 8 blocks or 16 by 16 blocks. And you should always think of all the operations need to happen at the block level. So in particular, specifically, if you access one out of a 16 cross 16 block, that has the same cost as accessing all 256 elements. Okay. And this is kind of the main thing that you really want to use. At least in TPUs, you can multiply two such blocks in constant time. This is kind of a huge saving. And in some sense, like very much geared towards what attention does, transformer does. And then you have multiple parallel compute, so you want to parallelize between them as well. And then you want to, again, as I said, avoid accessing slow memory as much as. All right, so doing a bunch of amount of flash attention, you put by tree, and again, you want to avoid access slow memory with apologies to tree because there's a bunch of other stuff happening in flash attention. But if I were to do one liner, it just says don't try to slow memory. And again, if you were in Christopher's talk yesterday, kind of talk a bit more about this. Okay, the second simplification that I'm going to do, instead of thinking of the MLP layer, which has this nonlinear thing, I'm going to drop the nonlinear stuff. So I'm just going to think of this matrix multiplication. It starts W. I'm going to make another simplification. I'm going to assume d n is equal to 1. So I'm just doing a d by d matrix by d cross 1 vector. Again, everything that I say here easily generalizes if you just kind of add on a bunch of stuff over here. And so in the worst case, matrix vector multiplication, d squared, again, you can't do much. And d by d matrix is really stored. So And the goal is, okay, so what this means is when I'm doing my training, I should probably not be learning on the space of all matrices, but maybe the distributed class of matrices where I'm guaranteed no space, no arithmetic operations. And so we want to kind of think of W as coming from some structured problem of matrices. And here are certain things that I posit are kind of necessary conditions, not the entire set of things you need to do. But you want these to be somewhat expressed. I mean, of course, I can give you the identity matrix, and that's all great and everything, but it's terrible for anything that you would want to do. But, you know, and some of this is kind of because we like to think about these structured matrices, but also like Fourier matrices and stuff have been used in anamorphic forms. It's not such an unreasonable thing to say. Well, the class that you contain should at the very least contain a Fourier matrix. Right? Then you could have doublets and something. The way you describe or parameterize this family has to be different because I want to use it in this. And what I want is kind of the matrix vector multiplication with the fast, what the fast means is smaller here. And at the end, I also want these to be nicely hardware managed. Yeah. So these are the four things I want to do. And again, the goal is if I get such a structure, the idea would be to replace the generic B cross B matrix with the structure. Okay. Since I'm only looking at a linear function over here, my arithmetic circuits without loss of generalities, especially over infinite fields, you only need to look at linear arithmetic circuits, only AX plus B. So I don't need any multiplication with two variables. The multiplication always has one constant. Okay, and so the two obvious choices, again, in this room, like what we do, the obvious things to think of are sparse matrices and low rank matrices. And I think these give what are called informer, performer, for example, if you were to apply this to the attention part. So by definition, both of these are great. I mean, they are kind of the reason you go for them is to kind of avoid this part time. But neither are expressive. So the discrete Fourier transform is neither full rank. Okay. Low rank actually turns out the way it's stated, it's nicely differentiable. If you think of this, it's a degree 2 polynomial in the entries of cube K. Polynomials are differentiable. Good. It's also hardware aligned because kind of pick like B by B blocks, 16 by 16 blocks. Sparse matrices on the other hand, at least the way we usually represent, which is just list all the locations of non-zero, is not differentiable. By definition, like very discrete structure. And it's also not hardware aligned. For example, if you pick random sparse matrices, stuff are all around. Even though the number of entries that you pick is small, you might hit all the blocks and then it might as well be. Okay. So here's another, so neither of two of our favorite tricks are not going to work here. So you can say, well, okay, I want like D squared arithmetic operations, and all of these, this is not a theorem, but pretty much all of, or at least any transform that I can think of that is efficient actually has a small linear arithmetic circuit. So maybe our definition of matrix class is set of all matrices that have small arithmetic. So I get the first requirement true by definition. They are expressive in the sense that we know a bunch of the stuff that we're interested in has small arithmetic circuit. In fact, that's what I spend most of my time. But it's not differentiable because the way you, again, the normal way you would represent the circuit is say list all the gates. Yeah, the input, two inputs to the gate, even if you assume bounded fan-in. Right? So again, it's a very discrete substance. It's not differentiable. And again, you know, things are all over the place. There is no reason to believe that it has some nice block structure and an arbitrary. So the thing is, all right, this doesn't work. But can I get something that's slightly larger, but now it's different? Okay, so that's what we're trying to do. So can we get a small enough superset of smaller arithmetic circuits? Well, why would this even be possible? So here's kind of the way to go. So again, let's go back to DFT. Here is, I think this is the two-layered arithmetic circuit for this. This is actually the what you get from the FFT if you apply to this matrix. And I don't know how many, unfortunately, this is not how FFT is taught in algorithms person, but you can represent FFT as matrix decomposition. Right? So this matrix is product of these three matrices. Okay, well, so what? Well, so it turns out you can reinforce this. And so here's a theorem you can prove. So if any matrix has a small arithmetic, what we are made by a small arithmetic circuit, the circuit can depend on the description of the input axis of it. Okay. So if you have any matrix, the corresponding linear arithmetic circuit is size and you can convert it into this matrix factorization, where the sum of the non-zeros is basically yes. And so if you do the obvious algorithm of multiply from the right one by one, the arithmetic complexity would, and the depth is exactly like the number of factors is exactly. Yeah.
How do you find these possibilities? So like, given W, how do you find it?
Given the circuit, you can find it.
Given the circuit, you can find it. The way you do it is, you can go both ways. If you give me a circuit, I can convert it into this thing. And of course, if I give you this, you get this.
Yeah, but
so it's not
this is not a drop-in replacement for an MLP. Like an MLP has two matrices. Doesn't have a circuit.
Oh, right. So in my head, MLP is just one giant matrix when you multiply both of them. So this is something we proved in the appendix of a paper. I've always asked this question. This doesn't seem like something that has
This is a corollary. I mean, this is easy, right?
it is easy in the sense that it turns out that if you want exact correspondence, you have to, it's not just the sum of n and z, but you subtract off the common dimensions. And so you do slightly more work, but it's not hard. I give it to undergrads who want to work with me as kind of the first problem. So this is easy. But I still do not know of a reference. This cannot be new to us. So if you know of a reference, please let me know so that I can start further. But yeah, this is working. Okay, so maybe this is it. But no, because you already know just one sparse matrix back. So taking product just makes it more. Okay. Is this a problem? No, if you work in polynomials, you know everything ultimately has to do with FFTs at the end. And so that's what we're going to do. So again, this is the matrix decomposition form of the 4x4 Fourier transform. The thing to note is if you look at the non-zeros, they're of course sparse, but they're also very structured. Right, so this is a permutation, which is like this bit reversal thing, it's very fixed. This is a 2x2 block. This is also actually a 2x2 block if you multiply on the left and right by something like a bit reversible. So everything is very structured. So we were like, okay, let's do this. So here is, I've just drawn, this is a 16-dimension DFT. I've just kind of dragged this places where there are non-zeros. So the way I'm going to think about my new class of matrices is, of course, in FFT or DFT, these are fixed values, but I'm going to make these parameters that you can know. And for good measure, it's going to stack on few of these. Okay, so this is now my class of structured matrices, a product of this sparse and structured matrices. And you just have to kind of learn these parameters. Okay. So fixed sparsity parameters, so I can run gradient descent. You can actually show that the last result that I said carries over in this setting as well. So any matrix with a small arithmetic circuit, you can express as a product of these butterfly matrices. You're going to lose some polynomial factors. But if your original circuit has polynomial depth, everything is correct up to polynomial. Okay. Okay, so the result more specifically is original thing was sizes and temp delta. You get these many arithmetic operations. It is expressive just because I told you that is true. It is differentiable because all the locations of non-zero things. So these, each entry is kind of a small pulse degree problem. It's not hardware. It's, I mean, structure is kind of, okay. But we are not that far. So the idea is you kind of look at these things and just kind of multiply the first two and last two. And then it turns out you can express them as block diagonal matrices, just permutations around. And the important point is these permutations are fixed. It depends on n, these are based on these bit reversal things. If you do the FFT thing, you get this bit reversal permutation just come multiply once. And so another way to think about this is you can think of the FFT that we learned in our undergrad algorithms course as being base 2. If you do it base square root it's instead of dividing 2 and 2 and so on and so forth. You kind of have this square root. So this is something called gives rise to what we call monarch matrices. And now the nice thing is you fit really nicely into your hardware, all block diagonal, just kind of doing the simple matrices. Okay, and so this is also hardware. Okay, fine. All right. So let's say we want to now replace attention, but I'm just gonna do so. Let's get more greedy because we know we can approximate attention by linear attention with kind of two tricks that I told you about. Linear attention can be represented as a non-linear representation. So instead of just trying to replace linear attention or attention, let's just try to replace all of it. So again, this is what we did for the MLP stuff. So we want to do something similar for any arithmetic circuit. So kind of two of the requirements I'll change. First, I just want this model to be simple, right? I can give you a horribly complicated thing with that. So okay, is there a simple kind of layered model that I can do? And now, instead of trying to represent just the matrix spectrum, any arithmetic circuit you start off, you want a similar result over here. Okay, so it's work led by Simran and Sabri. Actually, baseline doesn't even come in the abstract, so I just want to kind of opt this result off from section 3 in the paper to upfront, I guess. So again, I want the definition to be simple, expressive enough in the sense that any arithmetic circuit I want to compile into this layered model has to be differentiable. So here's the definition. You start off with your x, kind of do this linear math, right? Multiply on the right by the matrix. For technical reasons, I need this bias thing, which is again another n cross b matrix. Let's ignore it. So I get an n cross b matrix. I'll also do a convolution operator, which is I take another n cross b matrix and take column by column. The ith column here and also the ith column here. I get another n cross b matrix. I just take the Hardeman product. This is my definition. This is it. Okay. So hopefully this is simple enough. And in particular, the nice thing about since you can implement convolution with FFT, kind of the arithmetic complexity is basically tracked number of parameters. Okay, so is this expressive enough? And what we can show is yes. So basically, again, take any arbitrary arithmetic circuit, not just arbitrary linear arithmetic circuit, with size S and depth D, basically get up to polynomial factors, delta layers, next time set of parameters. It turns out like all of the work in the proof is actually done by the linear arithmetic circuit part, because you get the multiplication by this gating thing. And so all you need to do is kind of move things around so that everything lines up, which is a linear map. Okay, so it's expressive there. It's differentiable, if you remember about Strassman, that is true. But it's also, if you just look at it like, yeah, you need to hardware aligned. We just talked a bunch about how you can make this matrix vector multiplication hardware aligned, so that's true. This is convolution, do it with FFT. You can use the monarch matrices of FFT instead of base 2, like base 1 and a 4 and then you're doing this Hardeman product, but again, very simple. Though you can't use gems anymore. You can do it in parallel and speed it up. But it's not as fast doing this matrix multiplication. So, okay, I'm just going to say very quickly that if you look at linear regression, there were a bunch of papers that said transformers learn linear regression. We found out that depends on your definition of learn. And so, for example, if you say my definition of learn means if I'm solving AX equal to B, given A and given B, you want to learn X up to machine precision, then transformers can. So there's experimentally, and we have some kind of theory that's the case. But if you kind of try to learn like gradient descent on linear regression, again, low degree polynomial. So it turns out based on if you use both an experiment and theory, it actually goes down to machine precision. So I'll leave you with, sorry, 2 open questions. Please do something about gradient descent, do something nice. The other thing is the question that's really interesting to me is one of the reasons people don't want to use these new models is like you already spend a bunch of resources in creating this transformer, like you really want to spend that much energy again. But maybe you can distill or project down the transformer down. I think that's really like so. Basically, what I'm asking is there a version of SVD that they have a lower rank weighted program? Okay, I'm done. We were late in the game. If you are in the market or you know anyone who's on the market, we have up to 2 theory positions open. Please encourage, please apply or encourage. Yeah.
Just the last part, but have you tried training even like small models with this? Yeah.
Yeah, so these are actually pretty.
No, like, you can do it may not be the right way, but you can do a parameter count comparison, right? Like, your model is certain parameter count, take a transformer of the same parameter count.
Right.
As like a weak proxy.
Oh, yeah.
As like a weak proxy for like equally powerful.
Yeah, I think we do parameter.
No, so how does it perform?
Oh, like, so if you, again, like looking at the kind of error, if you track, the transformer things kind of stall at an MSE of 10 to the minus 7, whereas base con goes down to like 10 to the minus 13. But these are on very small sequence sizes. We're not talking about millions. Right? So the input sizes are really small. Good question. I think they're all like the matrices are all independent Gaussians. So, but yeah, that is an issue that comes up quite a bit. Like we were trying to extend these sort of reasoning prediction numbers. Yeah.
So I'm curious about the open question that you probably did. You said please prove something about gradient descent. Can you comment on like what do you think would be the simplest model that forces that gradient?
Okay, so I'm biased. I think you should prove this for base one. Right? But like even for very simple functions, like so here's one thing which actually came up in this linear regression stuff. You take a matrix U and compute component by square. You take a Hadamard product of U with itself. So you can show of course easily that in fact you can show things like under reasonable models of the test thing, the unique when gradient is 0, the unique thing is the answer that you expect. But we have no convergence results, right? So and in practice it works fine. But it would be really nice to have some sort of convergence results, even for these very restricted functions. I'm not talking about like language modeling and stuff. I mean, we don't have a good proxy for language modeling.
So, what's kind of the way that you're defining expressive or not? So like when you were initially talking about low rank, you're like, this is not expressive. And then you were saying for
Right,
every
so-
of a certain size, it's expressive.
Right,
Neither
so,
of those is like the full set of,
so here, when I say expressive, I mean, can you convert any arbitrary arithmetic circuit?
Right, but then that would require potentially large numbers of parameters or kind of,
Well,
right? To reach the full set of all of dense figure C, you would need.
yeah, but that's so, right, so of course, if you're kind of the inherent function, for example, if it's a quadratic linear type thing, then you expect to pay quadratic
Right.
stuff, right? And in practice, and again, slight hand wavy, most of these deltas are actually small. So you look at all of these transforms because they do this divide and conquer thing, and so the depth is always like log. So after log factors, everything tracks.
So is the argument that like for typical transformer weight matrices, you can get small deltas? I'm trying to understand, because neither of these are like fully expressive for the set of all matrices.
Well, yes, so, but what I want to claim is if there exists a low depth thing, then I don't know the answer to the question that you're asking,
Okay.
which is like, have we really kind of analyzed the specific matrices and see what the depth are? We don't.
Okay. I got it.